So is the LHC looking to see whether space itself is quantized or quantum? In a sense, yes, because, and again, this depends exactly what your question means. But once you start seeing quantum effects of gravity, and you might, in this example of large extra dimensions where there are gravitons that interact, types of gravitons that interact with us more strongly, in some sense, once you've gotten to the point that you're studying the quantum mechanics of gravity, gravity is really about the curvature of space and time. You are already starting to study the quantum properties of space-time at that point. So it is possible. However, that was one of those speculative ideas. And so therefore I would say, probably not, but maybe. It's not out of the question. What's the next big machine we want to see built? I want to see this machine produce something. And I want to know what it is before I answer that question. There are two reasons for that. This was a $9 billion machine. I knew why we wanted to build it. I don't yet know why we want to build the next one. I want to see what this one produces. I don't know whether we need a machine with higher energy, whether we need a machine with higher intensity. I don't know if we need a proton-proton machine or an electron-positron machine or something else. So I want this data. I want to see what we have in front of us, and then we'll start to make that decision. I think right now we don't know the answer. Yeah. Do I think the Higgs is a fundamental particle? And if not, do I think we would, and it's made from other things the way the proton is, do I think we need a larger collider to study those little things? I don't know about the Higgs being fundamental or not. Would I say, is it made from other things or is it an elementary field? I don't know. But I'm prepared to see what the data has to tell us. And in terms of how hard it is to see what it's made of, again, lots of possibilities. Hard to know. Yes?
I saw a YouTube video. I wondered what would happen if you stuck your hand in a Large Hadron Collider?
What would happen if you stuck your hand in a Large Hadron Collider? First of all, you couldn't, because the machine has all sorts of fail-safes. But if you somehow manage, and there's another reason you couldn't, which is that there's this beam tube. Right? The beam is running in a tube with a vacuum, which is better than the vacuum of outer space. There's all sorts of things about this machine which are just amazing. So that's another one. So if you could somehow find a way to get your hand in there without it somehow magically get through the beam pipe, or if somehow the beam got out of control and you stuck your hand out and they moved the beam out of the beam pipe somehow, it would burn a hole right through your hand like that. It's 100 billion protons. That's and that's in each bunch, and there are 100 bunches. They move the speed of light, basically. That's a lot of energy. So it would go right through your hand instantly. There's enough Earth above this tunnel that the beam cannot get out of the ground. But if you put your hand there, bad idea. Yeah. Could I say something about the unified theory of everything? It would be nice if there is one. How far are we from finding it? I don't know. One problem is we don't know if we know everything that there is to unify yet. I mean, it's nice to unify the stuff you know about, but if there's some more stuff out there, then you spend all this time unifying these things that you know about, and you discover this thing over here, whoops, back to the drawing board. I mean, so it's difficult to invent from scratch a unifying theory. A better way to say it is, look, we'd like to have a description of nature which incorporates all of the phenomena that we know about in as simple a framework as possible. We're not quite there, but maybe it's because we're missing some additional things we have to find out first before it's possible. And we just have to try. And if we fail, we'll also have the experiments going. Maybe the experiments will tell us something that we need to know before we can make that theoretical step. It's part of theoretical physics to try, and so far, we don't really know if we're on the right track or not. Let's see, where are we? I haven't been over here for a while. Yeah. Do I think that the rate of expansion of the universe relates in some way to the Higgs particle? The rate of expansion of the universe is a pretty complicated, well, okay, it's complicated in a couple of ways. One is that the rate of the universe, which was for many years thought to be gradually slowing down, as you might naively expect, was discovered in the late 1990s to actually be speeding up. This is what is known as the effect of the cosmological constant, or something like that acts like it, which is often called dark energy. It's not really energy, but it's dark, that's for sure. Okay. It's something which acts to push the universe apart. And we don't know much about that at all, and the LHC is unlikely to give us much insight into it, unfortunately. Although we could be surprised there too, right? I mean, we don't understand what's going on, so maybe there'll be a surprise there. But there is no reason to think that the Higgs particle itself has anything particular to do with dark energy, or that it has to do with the rate of the universe's expansion right now, or even that it had to do with a period of the universe known as inflation, where the universe expanded very rapidly and became the big place that it is. We think these are separate phenomena. There could be surprises, but that's not a place where I expect one. Okay. Yeah.
You said earlier that you explained how you know that the Higgs exists, or how you know.
How do I know that the Higgs field exists? Okay. So this is a little, let me think about how best to do this, especially given the time, and given how many drinks people have had. Okay. I mean, at some point, I have to retreat to the mathematics. Okay? There are certain things that we know because there's no other way to accomplish them within the context of quantum field theory. It's actually really hard to build a quantum field theory that works. There are all sorts of things that can go wrong. For example, if you take the standard model of particle physics and you just take the Higgs out and you try to leave all the particles there with the masses that they have, you can find processes that you can calculate whose probability of occurring is bigger than 1. Now, a theory which predicts anything with probability bigger than 1, or negative probability, for example, is a bad theory. And most theories that you can write down do that. It is not easy to find a theory that actually predicts probabilities that make sense. Taking the Higgs out of the standard model has that effect. So that tells us that there has to be something playing the role of the Higgs, although not necessarily exactly one Higgs particle doing that. Now, how do we know that there's actually a Higgs field? The problem is that if you take the Higgs field out, or set it to 0, there is no way to get the electron to be massless and the electron to be massive as we know it is, or to get the W particles and C particles to have the masses that we know that they do. We've measured these without mucking up the probability thing again. So you are driven by process of elimination to this one and apparently unique class of solutions. Of course, people are always looking for others, but in 35 years, no one's found one.
So the LHCs have the new sexy machine. What can you say about the Tevatron? Like what about its life cycle?
What about the life cycle of the Tevatron? This is the last question I'm going to answer, I'm afraid. I think a lot of people get tired, and so am I. The LHC is the new sexy machine. The Tevatron is its predecessor. And the Tevatron was running in various forms for decades. It was our big machine. It was the leadership machine. The United States is now ceding leadership in the field to Europe. And the Tevatron will be shut down in September. That's the end for US leadership in particle physics. But that machine did some very good things. First of all, it discovered the top quark, which we kind of knew was there, but we didn't know how heavy it was, so it found it. And it looked for many things that we thought might be there and didn't find them. It's a machine which got unlucky in a certain sense. It didn't discover many things it could have discovered. But it had a long and distinguished history. And its data continues to be very important in that it restricts the possibilities for what might be out there. The LHC, again, is exciting because it doesn't have the Tevatron's problem. The Tevatron couldn't cover all the possibilities for the Higgs field and the Higgs particles. The LHC has the reach, both in energy and in collision rate, that it can do things that the Tevatron simply could not do. It's got, right now, 3.5 times the energy. It will eventually have 7 times the energy. The collision rate is already several times higher. It will eventually be almost 50 times higher, 100 times higher. And so that will give this new sexy machine the opportunity to do what its predecessor simply couldn't. Okay. Thank you all very much. It's been a lot of fun.
Thank you. Let's hear it from Matt Strassler.